In the next few videos, we're going to take a look at using these EAS reactions onto benzenes that already have substituents. We're going to see that even the presence of one more substituent makes the process a lot more complicated. And when we have even more than one, it gets even more complicated. And so, let's start off with one of our simpler examples. Let's take a look at trying to brominate toluene. As we remember, toluene is methylbenzene, so it's benzene that has a methyl group. It's a very simple substituent. When we think about where we're going to put this bromine, we have three positions open to us, at least through symmetry. We have the ortho position, either the right or the left side of that methyl group. We have the meta positions, which are 2 carbons away, again, kind of the bottom right, bottom left sides. And then we have the para position, which is the opposite side. And when it comes to making the determination as to where our bromine should end up in our major product, we need to take a look at the sigma complexes. Magically enough, I have them here. Poof! Oh, whoops. For the most part, at least. All right. Let's take a look at the product that would be ortho, or rather the complex that would lead to the ortho position. As we know, we would form a carbocation through a normal EAS mechanism, and that carbocation is stabilized through resonance. That's what the sigma complex is. And as we see through these resonance contributors that we have a tertiary carbocation on the left, we have a secondary carbocation in the middle, and a secondary carbocation on the right. If we look at the sigma complexes generated through the meta position addition, all three of these resonance forms are secondary positions. And finally, if we take a look at the para positions, which doesn't look like all of them got through, we're going to see that we have a secondary position, a tertiary position, and a secondary position for that carbocation. And so, it's important to note that both the ortho and the para both produce a carbocation that is tertiary in one of their resonance forms. Thereby, those two are going to be more stable than the meta position addition would be. And as a result, our major product, we typically will see ortho and para. As to which of those, it all comes down to sterics. A methyl group is not very big, and we do have 2 ortho positions available to us, one on the right, one on the left. And as a result, because the methyl group is so small, we probably will get the ortho product as our major product, because it has a symmetrically identical position, so it really has 2 active spots it can go to. The para position, while free of steric problems, only has one. There's only one para position on the benzene relative to that methyl group, where there were 2 ortho positions. But again, since a methyl group is not a very big substituent, we're going to see that the ortho product will predominate here. As a rule of thumb, when we have a methyl group or smaller, that means we have 4 atoms or less, we're generally going to see the ortho product predominate. Anything with more than 4 atoms, so anything bigger than a methyl group, you're going to go to the para position. We're going to see that we have a variety of substituents that will guide other substituents to ortho or para positions. And again, the distinction there is all about sterics, whether they go ortho or para as your major product. And so we're going to see that anything that can add electron density to that position, like the methyl group does through hyperconjugation, will be what's called an ortho-para director. So, ortho/para directors. These will guide new substituents to ortho and para positions. And remember that kind of less than 4 atoms, we're probably going to go for ortho. And if we have more, we'll go to para as our predominant one. Again, this is a rule of thumb. We're going to learn synthetic tools that will have us selectively go on the ortho position or the para position. And so, rule of thumb for right now is a methyl group or smaller, your ortho will be the predominant major product. And if you have more than 4 atoms on your directing group, as we call it, you'll have the para product. And we're going to see that we can classify ortho-para directors in several ways. Well, directors in general, we're going to see that some substituents will guide new substituents to ortho-para positions. We're going to see a few others later on that will direct them to meta positions. And so it's simply a matter of learning what qualifies as an ortho-para director versus a meta director. And so generally speaking, these will be electron donating groups. We'll go over those further on. And we'll also include halogens here. Because halogens have very high electron density, they can help stabilize those carbocations that will end up on positions next to them. So electron donating groups and halogens will be our ortho-para directors. And we'll talk about those a little bit more in another video. By contrast, we're going to see a few are basically our only thing left, which are the electron withdrawing groups. Those are going to be meta directors. And so we're going to see that when we take a look at a meta director, we want to avoid putting the carbocations next to our electron withdrawing group. So we're going to see that electron withdrawing groups will be meta directors. If we take a look at the toluene example, we saw that if we put the bromine in a meta position, we ended up with those kind of secondary carbocations that could happen. So if we take a look at something like an electron withdrawing group on a compound, say a nitro group, remember that a nitro group is positively charged. And it's also got a negative charge on the oxygen, but what's close to the benzene is that positive. And so if we try and put the bromine on an ortho position, one of our resonance contributors puts the positive right next to the nitro group. That's a big no-no, right? We can't have two positives next to each other. That's a very terribly unstable situation. When nitrogen has a positive charge, it becomes extremely electronegative. It's going to try and withdraw electron density towards itself to balance out that positive. But now we're putting a site of poor electron density next to something that's going to suck up electron density. So that's a no-no. That's going to destabilize our molecule. So we don't see this happening. We, in fact, will see that in the case of para, we remember have one of the resonance forms that can put that on the top, this one right here. If we pretend that this is our nitro group up here, we're going to see that the para one does have a resonance form that puts that positive charge there. So that's also no good. But if we have our nitro group on directing something to a meta position, we can have our carbocations in one of 3 places. So we can have them either directly adjacent to the carbon to which the nitrogen is attached, or it can be the opposite side. So in either case, these 3 options, here's option 1, option 2, option 3, these are through resonance, and I'll just put the rest of the double bonds in here. Those 3 positions are far enough away that they're allowable. And so, suffice it to say, electron withdrawing groups are always going to be meta directors, because putting the new substituents in ortho or para positions will destabilize the molecule. But if we put things in meta positions, that doesn't destabilize as much, suffice it to say. So electron withdrawing groups are not so great for EAS to begin with, as we'll see in our next video. But if we have them on there, it's best for them to direct things to meta positions so that they can go through slightly more favorable transition states. And so, with this, in our next video, we'll talk about the effects of electron donating and electron withdrawing substituents on benzenes and their reactivity. And then further along, we'll talk about some examples in synthesis.